Hi, everyone. Thanks for joining us today. I hope you're having a great morning or afternoon or evening, depending on where you're joining us from. Welcome to today's webinar, Forecasting with Machine Learning Demystified. My name is Sabina Kadar. I'm going to be the moderator today. So we'll begin the webinar shortly. First, I'm just going to go over a couple quick logistics. So this webinar presentation is going to run around 55 minutes, and then we'll be saving time at the end for Q&A. So during the webinar, you can submit your questions using the Q&A function at the bottom of your screen at any time. So feel free to submit them as they come to you. We'll be monitoring these questions throughout the webinar, and we'll compile a list for Q&A at the end. We will also be taking questions submitted during the Q&A session itself. But again, if a question comes to you, don't feel the need to wait. Just go ahead and put it in that chat box. We'll do our best to address as many questions as possible. But if we do run out of time and we don't get to your question, don't worry. You'll receive a follow-up email at the end of the webinar. So we'll address everyone who does have questions. We also will be recording this webinar, and we'll be emailing you a link to the video sometime next week when it's available. The webinar recording will also be posted to both the Forecast Pro website and our Forecast Pro YouTube channel. And here you can actually find a full archive of past webinars. We have a ton of great educational webinars and content on there. So they're all free. It's a great way to catch up on anything you may have missed. Definitely recommend you checking it out. With that, I'll now hand it over to Sarah Darin to introduce herself and kick off today's webinar, Forecasting with Machine Learning Demystified.
Thank you, Sabina. So as Sabina has mentioned, my name is Sarah Darin. I'm essentially a lead data scientist here at BFS, which meant that I was pretty much in charge of implementing machine learning in Forecast Pro, kind of from like the selection of what algorithm we want to use, all the way through to the implementation and the automation of it in Forecast Pro. Really enjoyed doing that. So happy to share how we did that in this webinar. So with no further ado, let's actually kick off the webinar session.
AI has truly emerged as a transformational field that touches everybody. AI has allowed things like facial recognition, language processing, self-driving cars become a reality. And we've seen ChatGPT become an integral part of daily life for many. AI is so pervasive now that governments are very actively pursuing legislation on how to make sure that it's not used for nefarious purposes, something I am strongly in support of. AI is a term that really everybody knows at this point, and a lot of people understand the general framework, but the same is not really true for machine learning. Many people have heard of machine learning and realize that it's related to AI, but that's really about it. So I decided we should start off with a good, succinct explanation of machine learning and how it relates to AI. So naturally, I looked to AI to help me out. I asked ChatGPT this question here: what is the difference between AI and machine learning? I was using the microphone on my phone at the time, so what my phone first heard was actually, what is the difference between an eye and machine learning? The first application of AI by ChatGPT was to translate my question to the one that I intended to ask. And the answer that I got back to this question was not exactly succinct. It was 3 paragraphs long, but this last paragraph did capture the essence of the difference. In summary, AI is the overarching concept of creating intelligent systems, while machine learning is a specific approach within AI that involves training models to learn patterns from data and make informed decisions. Basically, ML is a subset of AI, and essentially ML-driven forecasting is a more specific term than AI-driven forecasting. But given that AI-driven forecasting may resonate more with the general population, it's quite reasonable to use that term instead. Essentially, it's probably just fine to use machine learning and AI-driven forecasting pretty much interchangeably. While ChatGPT gave us a good general overview of ML, let's dive into this question a bit more, perhaps with a bit more of a verified source. So what is machine learning? Machine learning isn't just one approach or method. It encompasses a wide range of algorithms and approaches. What these algorithms have in common is that they are designed to find and apply patterns in data. These methods can be broadly described in two categories: unsupervised and supervised. Unsupervised machine learning uses what we call unlabeled data to find patterns or associations in the data. Unsupervised machine learning is good for things like speech and facial recognition, market segmentation, things where you're trying to put data into like groups. Supervised machine learning uses labeled data, and it is actually used for prediction. Where does demand forecasting fit in? Forecasting is prediction, so we know that we want to use a supervised machine learning algorithm for demand forecasting. Let's take a closer look at the differences between unsupervised and supervised machine learning. Let's start with an example of how unsupervised machine learning works. So suppose your data includes images of different fruits, maybe apples and bananas. An unsupervised machine learning algorithm would analyze those images and identify that there are two different types of images and basically separate the apples from the bananas, but without knowing if each image is an apple or a banana, because we haven't told the algorithm that this is an apple and this is a banana. So the algorithm is unable to predict if a new image, an unseen image so far, is an apple or a banana. It can simply identify which of these two groups that new image belongs to. In a supervised machine learning algorithm, each image would actually be labeled as an apple or banana. In this case, we're really calling this whole input data set the training data. Instead of just separating the apples from the bananas, the supervised machine learning algorithm would learn how apples images are different from bananas and be able to identify a new image specifically as an apple or a banana. So we send the training data into a machine learning algorithm, we train a model, and then as new data comes in, as test data comes in, so new images, we're able to say that this is an apple and this is a banana. Again, because we're predicting and forecasting is a type of prediction, it really requires a supervised machine learning algorithm. So how do supervised machine learning algorithms work? Let's start by talking about a little terminology. If you hear data scientists talk about machine learning, you're likely to hear them talk about features and labels. Features are like explanatory variables in a regression model. Labels are like the dependent variable. So labels are basically what you're trying to predict or forecast. A machine learning algorithm might be able to automatically create features from an image, and a lot of people do try to do that with machine learning algorithms. But more often than not, data scientists actually really need to transform the raw input data into organized features themselves. So that's what we have here. We have taken those images of bananas and apples and created features that describe those images. So they capture a lot of the characteristics of those images, and then we have some labels. And this, of course, is the fruit type that we are actually trying to predict. So we're telling the algorithm exactly what each image is. So over here we have our features, for example, color, length, and shape, describing the images, and then we label those features with what type of fruit each is. This process of organizing the raw input data into features and labels is called feature engineering. Good machine learning models start with good feature engineering, and that means data scientists end up spending a lot of their time, a majority of their time actually, 60%, cleaning and organizing the data. So essentially doing all that feature engineering. As we embarked on implementing machine learning in Forecast Pro, understanding how we could actually automate feature engineering was really a key part of the research and implementation process. If you think about it more broadly, machine learning models have primarily been a tool for data scientists. Many companies have big teams, huge teams sometimes, of data scientists who are deeply involved in custom coding in Python or R these machine learning models. And they really need a solid understanding of both how feature engineering and machine learning work in order to generate these models, of course. Our goal in implementing machine learning in Forecast Pro was to basically take the data scientists out of the equation. We wanted to give Forecast Pro users the ability to use machine learning models for demand forecasting without having to worry about coding, feature engineering, or model refining. If you want to learn more about the details of how we automated machine learning in Forecast Pro, we delve into those details in our methodology workshop, an online workshop that we offer a few times a year, and actually we plan to start having some more in-person ones next year as well. But for this webinar, let's focus more on when should I use machine learning. So let's take a look at machine learning in Forecast Pro. When we first implemented machine learning, first and foremost, we wanted to make sure that machine learning could be used in an automated way, that you didn't need to be a data scientist to use it. And that's why, as we mentioned earlier, we automated feature generation from historic demand. So it is a univariate method. As an automated univariate method, that meant that it could potentially be also included in expert selection. For anyone not familiar with expert selection, it is our AI-driven automatic forecasting algorithm that really has always been the workhorse or brains of Forecast Pro since we released our first version almost 30 years ago now. So we actually really were on the forefront of AI technology 30 years ago. But just like people adapt, grow, learn, and get better over time, so has Forecast Pro's expert selection. So we do keep changing it as we see fit and where we see potential for improvement. Essentially, expert selection automatically selects the best forecasting methodology for your data. In order for us to include machine learning in expert selection, we really need to convince ourselves that it would be adding value. Expert selection is a really big part of the identity of Forecast Pro, and making sure that it truly was using the best methodology was kind of a cornerstone that we really needed to maintain. So we did some research, and essentially we determined that machine learning should be used for some data series often enough that it definitely made sense to include machine learning in expert selection. And you'll see that when we read in some data here and read in our bakery data, a data set that I suspect many of you may be familiar with, when I hit this read and forecast button here, Forecast Pro is going to automatically use machine learning to forecast all of the series and data that we've just read in. So what we're looking at here, our bakery data, has cakes and muffins, and that breaks down into customers and then further into SKUs. Now I'm going to go ahead and close our override grid here and go to our Reports tab and open up the item report. And what I can do in the item report here is, if you look through this, you can see that we have all of our items, and we list the model family for each of the items. And you can see machine learning coming up quite a bit. But what I'm going to do is I'm going to put on some filters here, and I'm going to select all of the items that selected machine learning, and I'm going to add them to the hot list. And I'm going to expand this up over here a little bit. So you can see here there are quite a few series where we end up using machine learning. So expert selection is selecting it as the best forecasting methodology for these series. You can see that muffins is coming up a bit more than cakes. But let's actually take look at some of the details of these machine learning models. So I'm going to close the item report. I'm going to add in the forecast report, and I'm going to add in fitted values. So let's just take a look at how it's fitting across some of these series. You can see actually the fit is quite good for some. Let's actually take a look at this here. And again, the reason I can tell that the fit is good is that this red line, so the historic fitted values, is actually trending relatively closely to the green line, the history for a lot of these series, and this forecast in particular here is looking pretty reasonable. The reason why we're selecting machine learning, though, isn't so much about how well it's fitting historically. It's more about how well it forecasts, and that's really the criteria that we're using for selecting machine learning. So machine learning is forecasting out of sample better, and that's why we end up using it. Let's actually scroll down to more details here, and you can see some terms like tree depth used, number of trees. We'll talk about the details of that pretty shortly. But for now, let's actually focus more on what features we're using. So here for carrot cakes, we have seasonal period listed first, and that's going to be what month it is. We have one period lag, so what were sales last month. Interventions. Interventions are a way for the model to automatically detect shifts in the data, spikes in the data. So if you have very noisy data, you're likely to see interventions coming into play in these models. Seasonal lag, what were sales last year, and then 1 year moving average. So these are the features, and they're ordered in this way for carrot cakes. And as we go through here, you'll see that the order actually changes a bit for each of these series. And we'll talk about why we're ordering them differently for each series in a bit as well. The main thing is the highest you are on this list of features, the more important that feature is for the forecast. When we read in this data, you probably noticed that there was a little dialogue that popped up that was telling us how many series have been forecasted, and it said that machine learning is enabled. Why do we have that dialogue? One of the things about machine learning is that it can take a long time. That's because machine learning is essentially analyzing the data and creating multiple models. So each model that the algorithm creates it then learns from the previous, it's learning from the previous model really to figure out what the best model is. If longer forecasting times are a concern to you, or after this presentation you don't think that ML should be used for your data, you can actually disable machine learning by going to Options and then going to the Performance tab here and selecting Exclude Machine Learning. So I'm actually going to go ahead and do that, and you can see what happens. So it says we're going to reforecast. It actually is happening quite quickly. And you can see now for chocolate layer cake, instead of a machine learning model, we have an exponential smoothing model. We include machine learning in expert selection by default because it does improve accuracy for many series, and many demand forecasters don't have the bandwidth to decide which series should use machine learning. That said, if we do disable machine learning in expert selection, you still have the ability to use automatic machine learning models wherever you might see fit. So what I could do is I could disable machine learning and expert selection, but if I think that machine learning might be good for chocolate layer cakes, I can select machine learning, and with a click of a button, I can apply that same machine learning model that expert selection had selected before. And we can do that, of course, for any of these other ones as well. What if we actually wanted to use machine learning and expert selection just for a few select series as well? We can do that too. We can go with the drop down here, and we can select expert with machine learning. And now you can see, instead of just applying that automatic machine learning model, we're actually using expert selection, and again, machine learning is coming out as the winner in that expert analysis. It also might be the case that you only want to use machine learning, for example, in one level of your hierarchy. So instead of using machine learning for all levels here, suppose I just want to be using it for the end items. I could go ahead and do that, and I'll apply this to this level. And you can see we're forecasting again with machine learning enabled for just those items. By disabling machine learning in those options, you can then manage where it's used in expert selection or as an automatic model yourself. Let's actually go back to the slides now to get more details about the Forecast Pro implementation of machine learning. Setting up features and labels is required for pretty much all supervised machine learning algorithms. But once you have it set up, there are a lot of different machine learning algorithms to consider. So things like neural networks, deep neural networks, support vector machines, random forests, the list goes on and on. And as you saw, at least suggested in the forecast report, we ended up choosing something a little different from this. We implemented extreme gradient boosted regression trees. Why did we do that? It's because we wanted to start by implementing a methodology that has been proven to forecast well. And extreme gradient boosted trees have performed very well in recent forecasting competitions, particularly the Macrodocus competitions. And those of you who are familiar with the Macrodocus competitions know that they're really considered to be essentially the gold standard of forecasting competitions. So the fact that extreme gradient boosting works so well in those competitions really held a lot of weight with us at BFS. Let's take a look at how a regression tree works with a very simple example. Here we have a very simple tree, and it's using two features. So we have month and we have sales last year. So we're generating a forecast value based on the values for these two features. How do we do that? Well, let's take a look at some examples. Suppose we're forecasting September 2023 and sales in September 2022 were 350. We start at the top of the tree and we ask, is the month November or December? So is the month greater than or equal to 11? The answer to that question is no. And that takes us to another node and another question. Were sales last year greater than or equal to 400? And again, the answer to that is no. And that takes us to a final forecast of 300. Let's take a look at another example quickly. So now, let's suppose that we're forecasting for October 2023, and sales in October 2022 were 450. Again, October is not November or December, so the answer to the first question is no. But now, sales last year were 450, so the answer to this next question, were sales last year greater than or equal to 400, is now yes. And that takes us to a forecast value for October of 550. A few other terminologies that might be useful coming from a regression tree include things like tree depth. What is tree depth? You saw it on the Forecast Pro forecast report. Tree depth is the length of the longest path from the top of the tree to the bottom of the tree. So in this case, that's the number of arrows going from the top to the bottom, and the longest path is going to be equal to 2. The higher the tree depth, the more complicated the tree. And we'll talk about this a little bit more later, but the general idea of training a model is you want to make it as simple as possible while still forecasting well. So keeping down the complexity is generally going to be a good thing. Some other terms that you might see, not so much in the forecast reports, but a bit in machine learning literature, is split nodes and leaf nodes. Split nodes, the blue ones, are also called decision nodes. These are where you have a question and you're moving on to another node. The leaf nodes or terminal nodes are the ones that are going to have the final forecast values. So what are extreme gradient boosted trees? Regression trees are essentially the building blocks for extreme gradient boosting. That's because extreme gradient boosting is an ensemble method, which means that we're taking the average forecast across multiple models. Ensemble methods have generally performed well in forecasting competitions, such as the MacroDockers competitions, particularly for automatic forecasting. The models that we're averaging across are regression trees, and extreme gradient boosting really focuses on finding simple trees in order to avoid overfitting, which we'll talk about in just a minute. But avoiding overfitting is really important for forecasting and really modeling in general. If we think back to the data scientist slide and how they spend their time, feature generation was a huge part of it, 60%, and we have automated that. But another part is figuring out the right parameters, tuning the model. For extreme gradient boosted trees, the two most important parameters are maximum tree depth, so how complex can each tree be, and the number of trees, or the number of models you're averaging across. Using trees that are too complex or using too many trees can easily lead to what is called overfitting. Overfitting means that your model fits your data well historically, but it doesn't forecast well. In order to automate extreme gradient boosting, we needed to automate how to identify the tree depth and number of trees that forecast most accurately. So we did that using very similar AI-driven techniques to those that power expert selection. We're not going to get into the details of how we optimize gradient-boosted regression in this webinar, but if you are interested, we do review those details in our methodology workshop. Let's go back to Forecast Pro and take another look at the forecast report. So here we are back in Forecast Pro, and what we're looking at here is carrot cakes. Let's look at more closely at some of the model details in the forecast report. So Forecast Pro for carrot cakes generated a automatic machine learning model that has a maximum tree depth of 2 and it's averaging across 14 different regression trees. So this is a pretty simple model. If we choose a different series here, we'll see that there's a different number of regression trees being selected. Tree depth is actually the same, although if we go to yet another series here, so another chocolate cake series, we can now see that a tree depth of 3 is being selected and the number of regression trees is 139. The point is that Forecast Pro is automatically detecting, using its AI-driven technology, it is optimizing the tree depth and the number of trees to use for each individual series. The other thing that we already mentioned varies from one series to the next is the order in which we are listing these features. The way we're listing these features is by importance. So the most important features are listed at the top, the least important at the bottom. So in this case, seasonal lag, what sales were last year in the same period, is the most important feature. And that again is going to change from one item to the next. This next item here, it's actually what sales were last month is the most important feature. How are we determining importance? For this webinar, we're not really going to get into that too much. If you want to have a better understanding of how we're measuring importance, again, we recommend that you consider taking our methodology workshop to get more details on that. Automatic forecasting is really a workhorse of the forecasting process. Typically, you start with automatic forecasting and then identify which series need more customization. Sometimes the customization includes just changing the univariate method used, but more frequently there's other information, things like promotions, price changes, or stockouts that you want to incorporate into your forecast. One of the strengths of machine learning is that it allows you to include features that incorporate domain knowledge, things like price changes, the weather, and the economy. While Forecast Pro machine learning algorithms automatically generate features for univariate forecasting based on the historic demand, it's not going to be able to automatically generate features to capture your domain knowledge because it simply doesn't have access to your domain knowledge. You need to tell it. So in order to integrate your domain knowledge, we created what we call custom machine learning models. Custom machine learning models allow you to include things like events and explanatory variables in your machine learning models. The idea is these events and explanatory variables are a way that you can read in your domain knowledge into Forecast Pro, and then Forecast Pro is able to use these variables, these features, to forecast, to include in your custom machine learning model. So let's actually take a look at how custom machine learning models work in Forecast Pro. So we're moving on now from bakery data to mouthwash data. So this is another data set that's installed with Forecast Pro. So if you do have Forecast Pro installed, it's available to you. And it includes 2 SKUs of Minty Fresh mouthwash. And we've also gone ahead and read in a couple of helpers, so event schedules that integrate some domain knowledge about this mouthwash that we'll get to shortly. But before we do that, let's actually take a look at the historic demand for the 24-ounce bottle. If we look at these spikes here, and these spikes really are what catch your eye when you look at the data, let's take a look at when they're happening. This first one is in May, then October, then January, May, October, January, July, October, January, July, October, January. So we're seeing that there's a shift when these spikes occur. So this is an example where you really want to be thinking about domain knowledge. Why are we seeing these spikes? Is mouthwash seasonal? No. The use of mouthwash is probably pretty consistent throughout the year. It turns out that these spikes are actually driven by price specials. And that is why we have called our event variable over here price specials. If we take a look at that event variable, we can see that these price specials are pretty well aligned with when we saw those spikes. So we have October, May, and January coming up, and then even we see the shift happening in this event variable as well. This is a good example of data where in order to generate a good forecast, we really need to account for when these price specials are happening. So I'm actually going to go ahead and go back to our SKU here, and I'm going to put in the forecast now. What you can see is that we're not really seeing the spikes in the forecast horizon. There's some movement up and down, but not a whole lot. The model we've selected, we can see, is a machine learning model. And even though we actually see seasonal lag as a pretty important feature, when we look at the forecast, it actually looks a little bit like the model is learning that the spikes aren't really seasonal. But in the absence of other information, such as the price specials variable, the spikes are attributed a little bit to seasonality and a little bit to noise. If we look at an exponential smoothing model instead, you can see now the exponential smoothing model really is considering these spikes to be seasonal, and we see that in the forecast horizon. Bottom line, though, is both of these models, both the exponential smoothing model and the machine learning model, are generating bad forecasts. In order to generate a good forecast, we really need to account for when these price specials are occurring. So we need to incorporate our domain knowledge about when the price specials occurred in the past and when they're occurring in the future into our forecast. Let's go ahead and do that. Let's start actually by trying out an event model. So I am going to go ahead and I am actually going to build an event model with just this price specials event. And what you can see now is in the forecast horizon, we do have spikes happening the 2 times when we have price specials occurring during the forecast horizon. But we can also see that the forecast is pretty flat between when those price specials are happening. So let's take a look at what happens with machine learning. So I'm going to come over here and select my custom machine learning model. And when you see this, you can see that we have the ability to name various models. We also see sections for specifying events and explanatory variables. We don't have any explanatory variables read in right now, so this box is empty. So what I'm going to do is I'm going to select price specials. I am going to go ahead and use automatic for helping us determine the right number of trees and the right maximum tree depth for our models to use. And I'm going to go ahead and hit apply. When I do that, you can see the forecast shift a bit. In particular, what you can see is we still have these spikes happening when the price specials happen, but we also see these dips happening after the price special. Why is that? The machine learning algorithm is basically learning that after a price special happens, you very often are seeing a dip in demand right after that promotion. And that's actually pretty common after you have a promotion. People are going to move up their purchasing of something, and that causes post-promotional dips. The machine learning algorithm is figuring that out on its own. So we're not telling the machine learning model to look for that dip, but it is, in fact, finding it without our having to do so. So you can see here that in the forecast report, price specials are actually the most important feature, and the percentage of the model accuracy being contributed to by price specials is particularly high at 91%. I'm actually going to go back to our custom model here. An advantage of machine learning models using events is that you can actually use multiple events. That's something that you can't actually do with event models. For machine learning, you can select however many schedules you might want, however many explanatory variables you want. When the machine learning algorithm runs, it's actually going to only use the variables that are going to help improve forecasting. So as an example of that, let's actually take a look at this schedule 01. So I'm going to actually cancel out of here, and let's take a look at this schedule. What this is, basically, is it is an event schedule that has a single event happening on April 2020. And I'm calling this a non-event because if we look at April 2020 in here, it's actually right here, nothing really happened in there. So including an event schedule with a single spike there should not be an important driver for the Minty Fresh mouthwash sales. So let's see what happens when we add this into our custom machine learning model. So let's go back here, and we now are selecting the schedule 01, and let's go ahead and hit OK. The forecast didn't change, and the model didn't change. The schedule 01, the non-event, is not even being used by the machine learning algorithm. It is not included in our final machine learning model. The machine learning is actually doing a good job of model specification and only using the variables that actually make a difference to our mouthwash demand. That's great, but there are also some drawbacks to using event schedules in machine learning models instead of event models as well. When we look here, we can see price specials are indeed a really important feature, but we don't really see what the impact of the promotions are on demand per se. If I switch this over to an event model now, we can see exactly what the impact of the promotion is. We see an index of 2.169 right here, meaning that when a promotion happens, we see sales a little bit more than double. And that's just not information that we can get out of the machine learning model. With that, let's actually go back to our slides. Let's talk about some of the pros of machine learning. Machine learning often forecasts noisy and low volume data better than traditional time series methods. This was the case when we looked at the bakery data. When we took a look, we noticed that muffin series were being forecast with machine learning more often than the cake series. If we looked more carefully at that data, we would also notice that the muffin series are a lot noisier than the bakery series. So this is something that we see across a lot of the series that we've tested, that machine learning typically is popping up a lot more and is more useful for noisy and lower volume data. Machine learning allows you to use key sales drivers such as explanatory variables and weather. This is really important, and we saw a good example of that with our Minty mouthwash. Machine learning does not require variable selection and specification. Again, we saw in our Minty mouthwash example that Machine learning is doing some of the variable selection for you. The models are only going to use the variables that are deemed important to the model. Machine learning can automatically account for outliers, and this is somewhat related to our first point about noisy data. It is one of the reasons why machine learning can be very useful for noisy data. Machine learning can automatically handle missing data. This is certainly very useful. It's a big problem in forecasting in general that a lot of models, particularly ARIMA type models, really need to have all of your data there. And then finally, and this is probably the most important of these, machine learning can account for multiple cycles. So if you have daily data, if you have hourly data, if you have every 15-minute data, or even if you have weekly data, you're going to have multiple cycles. What we mean by multiple cycles, so for example, if we think about daily data, you're going to have a within the week cycle, and you're going to have a within the year cycle. If you're only forecasting out a couple of weeks, that might not really matter. Because the seasonality is not going to change a whole lot in your forecasting horizon. But if you're forecasting out longer, you're likely to want to account for those multiple cycles. Let's actually take a look at an example in Forecast Pro of data that really benefits from Forecast Pro's ability to identify multiple cycles in machine learning. Let's take a look at a little bit more data. And again, this is some new data, and this is actually hourly data. It is inquiry data, so hourly inquiries. Right now, we're just showing the historic data. And one of the things that really stands out is obviously within each day, there is a very strong within day cycle. But we also see a within week cycle with the first 2 days here having many fewer inquiries than the other 5 days. I'm assuming that these are weekends and these are weekdays. You'll also notice that we have a vertical line down here. That's because for this data, what I want to do is compare how well machine learning works for out of sample versus an exponential smoothing model. So the data over here, this historic data, we're going to reserve. And what we're going to do is we're going to compare the forecast generated by the data on the left-hand side to the historic data that we have here. And that's what we're doing when we do out-of-sample forecasting. So currently, we have a machine learning chosen. That's what expert selection selected, and you can actually see if you compare this cumulative MAD here, it actually looks to be drastically better than exponential smoothing. So let's go ahead and add in the forecast. And we can see that, in fact, the machine learning out of sample forecast seems to be doing very well. There's not a whole lot of difference between the green and the red lines. So this is a really good forecasting model. Now let's take a look at the alternative, so exponential smoothing. So I'm going to come over here and just use automatic exponential smoothing. And what you can see is when we use exponential smoothing, we are only capturing the within day cycle. We are missing the within week cycle. And on these two, on Saturday and Sunday here, we are drastically overestimating our inquiry demand. You can also see that with Box-Jenkins. Box-Jenkins, a little bit better, but also not doing a very good job of forecasting. So this really is a good example of how much better machine learning is going to forecast multiple cycle, particularly these very strong multiple cycle series, than some of the more traditional forecasting methods. Now let's take a look at some of the machine learning cons. First up, and quite importantly, machine learning is computationally intensive, so processing time is considerably longer than traditional time series methods. This might be okay if you don't have a whole lot of series in your project, but if you have tens or 50,000s or hundreds of thousands of series in your project, you're going to need to either allocate the time and be patient for the model estimation, or you're going to want to think about maybe turning off machine learning for all series. So disabling machine learning and expert selection, and instead using it only for the series that really need it, or perhaps using it for just one level of your hierarchy. Machine learning focuses on forecasting, not explaining relationships. When you do a regression, you're going to get what we call a coefficient that basically tells you how your sales drivers impact your forecast variable, your demand. Or when we looked at the event model with Mouthwash, we were able to get an event index that told us how much higher sales were when a promotion was running. We don't get that with machine learning. Yes, we can see the relative importance of a feature, but we don't really see the impact of that feature on sales. And that really leads us to this next point, that because it focuses on forecasting and not explaining relationships, it can be hard to understand why a machine learning forecast is what it is. Very often an explanation makes us understand and see why a forecast is what it is. Machine learning is a bit more of a black box. Extreme gradient boosted trees don't extrapolate trends, although we are working on ways that we might be able to integrate trends into our forecast a little bit better. In terms of trends changing, if you're looking at a forecast 3 to 6 months out or even a year out, it's unlikely that the trend is going to have a really big impact in that forecast horizon. So for the most part, this has not been a major problem for those kind of medium-term forecasts. But if you're forecasting out longer, or if you have a very strongly trended series, machine learning is unlikely to work well for you in its current form in Forecast Pro. So when should I forecast with machine learning? When you have important demand drivers, when you want to integrate domain knowledge into your forecast. Machine learning can be much easier to work with than something like a regression model because it really handles a lot of that variable selection and model specification. It's much more straightforward to integrate domain knowledge into a machine learning model than it is to a regression model. When your goal is to forecast, not explain the relationships between features and demand. When you have frequent unexplainable spikes or complex patterns in your data. This again goes to one of the pros of machine learning being that it works well with noisy data and it has some built-in outlier detection. When your forecast should fall within the historical range, so it's not very trended. And again, this goes towards one of our cons that currently extreme gradient boosted trees do not handle trends very well. And if it is heavily trended, then again, you probably should think about using more of the traditional time series methods. When you have data with multiple cycles. So we just saw how much better machine learning works with hourly data, and that is also the case for daily data. And typically, even if that data is not noisy, even if it's very regular, if you have that granular data, machine learning very likely is going to do better than traditional time series methods. And simply put, and probably a bit obvious, but when machine learning outperforms other time series methods. So you don't really know how machine learning is going to do until you actually try it. Really, at the end of the day, the best way to decide what model to use for your data is to do some out-of-sample forecasting and compare the various models on your own. And if you find that machine learning helps, then by all means, go ahead and use it. So that concludes this presentation on machine learning and when you can use it and when you should use it, that is. And I hope it has proven very helpful.
All right. Thank you, Sarah, for that great presentation. And we do want to apologize for the blurry quality. It looks like we ran into some bandwidth issues despite our best efforts. So really appreciate your patience and sticking with us through it. We'll be getting to the Q&A portion in just a minute. Just a reminder, if you haven't already, go ahead and put your questions down in that Q&A box. But first, I do want to remind you again, this presentation today is being recorded and it'll be posted to both the Forecast Pro website and YouTube channel. And we'll also be emailing you next week when the recording is available to view on demand. We do also have a couple events coming up in the new year that we just want to let you know about. First off, today's webinar is part of a quarterly educational webinar series. We're still locking down the details, but typically our Q1 webinar is the third Thursday in January. So you can expect it to be around then, and we'll share more details as we have them. We are also starting a new webinar series in 2024 that's going to be a little more focused on Forecast Pro and the product itself. We actually would love to hear some of your feedback. Obviously these webinars are for you to make sure that they're valuable information. So I'm actually going to put a poll up on the screen right now. If you do just want to give us your thoughts, would you be interested in attending this? Are there any topics you want to see? And like I said, those details are also being worked out right now, but we'll share more with you as we have it. And then finally, Sarah mentioned in the presentation, we do these business forecasting workshops that are a little more focused on the methodologies, forecasting methodologies and techniques. The last couple of years, we've been doing them online just because of COVID, but we are working to do them in person again. So the next one will likely be this coming winter. It's looking like February in the Orlando, Florida area. So again, stay tuned for information about that. Just a quick overview of that business forecasting workshop. They're 3-day seminars, and they give a really good overview of various forecasting methodologies and techniques. They're great if you're new to forecasting and looking to get a good foundation on kind of everything that goes into a forecasting process and some best practices. Or it's also really valuable if you're experienced and you're looking to improve your forecasting process or maybe throw in some new, more advanced methodologies. So again, stay tuned for all of those events and more information as we get details locked down. And then finally, before we get into Q&A, you did see Sarah use Forecast Pro today. That's the software that Business Forecast Systems makes and sells. So if you do want to learn more about the software, reach out to us. You can either put it in the chat box and let us know that you'd like us to get in touch with you. There will be a survey pop up at the end of this webinar. You can also request a demo there, or go ahead and visit our website. You can scan this QR code and either request a demo, or we also have free trial software downloads if you want to test it out. So with that, I will get into the Q&A portion. We're at the end of our official scheduled time, but we'll take a couple minutes for those who are able to stay on and get to your questions. And again, if we don't have time to get to your question during this webinar, we'll follow up with you by email, so don't worry. So with that, Sarah, let's get into some of these questions. I'm actually going to stop sharing my screen just so I can read them a little easier. So let's see. It looks like the first question someone asked, does machine learning provide tweaks to the forecast based on actuals to improve forecast accuracy?
Good question. And one that we actually get a lot. There is a little bit like how is the algorithm learning exactly? So in a way, yes. If we went into the details of how gradient boosting works and this kind of adding one model at a time, the way these trees are built, the multiple trees, is each tree that is added to a model is designed to improve on the accuracy of the previous model. So for any given machine learning model, that kind of forecast accuracy improvement along the way to develop the model is integrated. The way, though, that a lot of people expect it to work, that it doesn't quite work, is, so right now we're in October, you have a machine learning model developed in October, you add a month of data, and and the question is, are we looking at what happened specifically in October with the machine learning model that we built in October to improve? And it's not exactly that. What we're doing in November at that point is kind of like starting a new machine learning model from scratch, very similar history, and the same method where each tree that you're adding is looking at the accuracy of the previous trees to come up with the final machine learning model, but it's not really explicitly looking at the previous month. So that was probably a bit of a complicated answer, but I hope it does make sense.
Definitely.
So next question.
Yeah. Let's see. The next question, someone asked, how long should the historical data be to have a good forecast with machine learning? Should it be 24 months? They said they tested with only 12 months of historical data and it was a straight line.
Yeah. Okay. So first of all, 12 months, you're going to get a forecast. And it's probably going to be a reasonable forecast. It's almost certainly going to be a flat line. The reason being that you can't come up with any type of seasonality from 1 month to the next when you have only 12 months of data. So the what machine learning is kind of doing is coming up with the best place to put that straight line, honestly. When it comes to the recommended length of data, the more the better. 24 months is minimum, I would say. 36 months is ideal. And again, if you're dealing with monthly data, if you think about the bakery series, which is 36 months of monthly data, obviously, machine learning works on that data, but it's not necessarily a ton better than traditional time series methods. For some of the series, it's a lot better. But once you get into different types of data, once you have a much longer time series, once you get into weekly, daily, hourly data, and that usually means a lot of data, is when you see the real differences and the real advantages. So basically, it's okay to use machine learning with these these shorter data sets. But what you see coming out of those models, it's going to be reasonable, but it's not going to be as drastically different from what you're going to see coming out of traditional time series models as it would be for much longer data series and much more frequent with higher frequencies. Okay.
Let's see. I am keeping an eye on time. I want to be mindful. I know we're over it, but we got quite a few questions, so we'll try to fit a couple more in.
Sure.
So going on to the next question, someone asked, how could potential machine learning overfitting be factored into comparing with other methods? So for example, expert selection, increasing depth and number of trees could lead to machine learning being chosen over other methods most of the time.
Okay, so there is overfitting that can come about if you have too many trees, and that's definitely true. The way, though, that expert selection works is, so that overfitting is happening in the within sample. So when you see overfitting, which, it basically means that your historic fitted values are going to be very close to your historic actual. When you see that happening, it can be concerning. But when we're doing the model selection, when we're deciding, say, machine learning versus Box-Jenkins or exponential smoothing, we're not looking at that within sample. So in a way, it doesn't really matter that overfitting is happening within sample. We're only looking at out of sample. So that's basically why we don't end up choosing machine learning all the time. That said, when we do see those cases of a lot of overfitting, it does, like, it does also make me a little bit nervous, and I'll sometimes take a look at that particular model and say, are other models consistent with the forecast that's coming out of this? And at times, like with everything, sometimes I'll say, even if expert selection came up with this, maybe this isn't the model that I think is best. So in terms of the overfitting, I don't think it's a major concern, but in terms of the way that expert selection actually works. That said, when I do see a model that appears to have overfitting come out of expert selection, I sometimes actually will take that extra time to make sure that it really is a good model for the data. I would say most frequently it is, but I understand that kind of little double check inclination.
Great. The next question I'll ask is also related to expert selection, so I think it's a logical transition. They ask, is machine learning with explanatory variables and events available in the automatic expert selection model?
It is not available in the automatic expert selection model. And the reason for that is our automatic model does not currently include external data, as we call it. This is a great question, because this is something that we talk about internally a lot, that how should expert selection kind of adapt and morph? In the introduction, I talked about we've been around for 30 years, but like expert selection keeps changing. That's very much true. And one of the ways that we see it changing is to actually be able to specify that you want expert selection to consider perhaps all of the explanatory variables or all of the event variables that you have in your project, to be able to consider them as variables in not necessarily just machine learning, but in event models and regression models, and using them to decide with those external variables which of these methods is best, or maybe you don't want to use any of them, because sometimes including external variables just makes things a little bit noisier. But yeah, that's a place that we would like to go. But currently, you have to create a custom model to include them. But you do get the automation of the tree depth and the number of trees in that customized model. So partially automated.
Yeah. All right, we'll try to fit in a couple more here in the next few minutes. So the next question is, can a user dampen or increase the use of seasonal index using the model properties, or can they only do this by adjusting demand history? Well,
first of all, adjusting demand history would certainly get you there. And the short answer to that is no. Currently, the way machine learning is implemented here is to basically let the algorithm decide the relative importance of the seasonal index and things like that. So machine learning is going to come up, not exactly the index, but an implied index within the model in terms of that automated variable selection process. So and that automated variable selection process kind of is the central thing in my answer of no. So one of the central things in the way we've implemented machine learning and how it works actually in something like, XGBoost or whatever, is that automated variable selection. So letting the algorithm actually go through the work of, figuring out what the best variables are. So we kind of let it go with that. So.
Perfect. And actually, I think we'll probably end it there just because,
Okay.
again, we are well over time. Want to be mindful of people's days. But for those of you who submitted questions that we didn't get a chance to get to, again, we'll follow up by email. So don't worry, it will be addressed. But again, just want to be mindful of your day and not hold you. So thank you so much, everyone, for attending today's webinar. As I mentioned earlier, we have some other events coming up in the new year. So we'll let you know about those by email. And then also, as I've mentioned, we'll send you an email next week with the recording to this. So, Sarah.
Thank you, everybody.
Yeah, thank you
Have a
so
great
much
rest
for
of
all
the
you've
day.
done. Yeah. Bye, everyone.